I'm waiting for the grade to learn who this grader is.
So hopefully everyone got their first exam, right? The only surprising comment I found when I was grading that was some people confuse APIs with the system calls and the privileges and stuff, right? So basically, API call is just a sugar coating around the system call. It doesn't do anything with privileges or what have you. So for example, if you have a system call called clone, right, we'll see that later in the class today, right? You may have API call called fork, which does something and invokes this system call and gets back. But it doesn't do anything to the privileges or anything, right? If this is running in user mode, it'll continue to run in user mode till it hits here. The system call is the one that matters. The API call is basically a library function. So API calls cannot magically give you more privileges. And that's why you have to do special instructions or what have you to move from user state to kernel state. Many of you answer that if you use API call, then you can get privileges. If you use these, privilege instructions to call API call. So API call is no more than a library, right? So that, hope that is clear. So API calls do not change anything. API calls are just making this stuff a little easier to use, right? Other than that, that's the sort of distribution, and you probably have the same handout too. So it's graded out of a 60. Only one got a 60. So if you might have noticed that some of you got the right true or false, but got a lower grade. Some of you actually. So I think few of you gave an excellent reason of why it's false, and then you answered it as true, right? And so I think I took a little bit grade, not a whole lot, right? So, but some of you answered false and gave a reason which is not convincing. Some of you gave a false and gave a wrong reason, right? Some of you gave a false and gave a reason which is not true at all for operating system. So, for stuff where you are giving a completely wrong answer, I actually took out a lot of points because at the end of the day, I had to doubt your how much you understand of what is being asked, right? So, like I said before, the any addition errors, talk to me immediately. Others, give me a reason why you think your answer is valid, right? Because if I'm making a judgment call based on how the rest of you did, and we can take a look at that. So the bottom graph is basically the percentage grades of where people stand. Again, these are not correlated, so whoever got the highest does not mean that they're here. They're sorted differently, right? So far, this is sort of how the grades look after the homework assignment and the homework midterm exam. So the project should be due today, right? So if you have the hard copy, please pass it to the front, then you get a chance. So today we'll look into how Linux kernel does some of the stuff that we've seen so far, right? It's more topical than what the class talks about. The class talks about more in general, and this will give you a hint on how an operating system, how a modern operating system behaves, right? And we have only one lecture, so I'm going to go through a brief overview of what things are. And when you compile the kernel and stuff, right? So now you know how the kernel is in a very, at least a little bit, right? So most of the files that we're going to look at are in the directory kernel/sched.c. That gives a scheduler. So feel free to go and look at that. In fact, I encourage you to go look at it to get a sense of how these things play out, right? And so that said, Linux. So far we looked at processes, threads, and scheduling. So we wanted to see how processes map into Linux, right? So Linux calls processes as tasks. So it has a structure called task struct, which is basically your process control block, right? So it keeps track of all the information about a running process. And if you look in the inner kernel source, include linux sched.h file, right? The header file will have the struct for the task struct, right? So whenever a new process or task gets created, you have to allocate the task structure, and it's large. I mean, it's 1.7 kilobyte on a 32-bit machine. On a 64-bit machine, obviously it'll be bigger because the ints are longer, right? But so the kernel has to figure out where to allocate the structure. So if it's that big, it has to reside somewhere. So so how many of you actually have the textbook? Okay. So if you're not required to have the textbook, and so the source code is actually the best way to look at what's happening in this particular aspect, right? So when you implement the operating system, you have to figure out where this data structure goes. So you can either allocate it when you boot up the kernel, or you can allocate it on demand. So if you allocate it where it should go, depends on how the operating system is organized. We haven't looked at memory management yet, so we're not going to go into that detail, right? So it also has a notion of a thread block, which has pointers to the task infrastructure. And the latest kernel stores the thread info on the kernel stack of the process which is running it, right? So it basically uses the process to store its state. So it stores it in the kernel stack itself, right? So that it avoids keeping in kernel data structures. So process IDs in Unix are a 16-bit number, and uses up to 0232767 as the process ID. So that's the number that a Unix kernel exports the user to identify a process. So a process can only be up to 32768, which means that at any particular instant, you can only have that many processes running, right? Which may be a small number or a large number depending on what you're trying to do. So if you're a server like Darwin with lots of users logged in, that may not be a large number because it'll wrap around fairly quickly, right? And you can, of course, change that number to whatever you want. Now that you have this kernel source, right? You just modify some variables, recompile the kernel, and you have a different kernel which will do what you want, right? And of course, you'll break some other piece of code, but so that's that's part of what you try to do, right? So it maps into what Unix's notion of 32767 is, but Linux itself does not really care how big that number is, right? Based on how much space it has. So the task can be in Linux can be in one of those states, right? So let's see how that maps into what we looked at before. So task running means a task which is either running or it's runnable. So if a task is waiting for a CPU, it will be the task running state, right? And depending on whether it's allocated, it can be actually running or waiting the wait queue. And task stopped is when you stop a process through user notion. So user can send a signal called stop to basically stop the process. So the process may be it may be possible for it to run, but for some reason you just stop the process. Task zombie, I'm going from the bottom. Task zombie states that once a child is finishes, right, it has to wait for giving its status to its parents. So task zombie basically puts a process in a state where everything is done, all the resources have been taken away. It's just hanging around to give its status to the parent, right? So it's in a state where it's not consuming any resources, but it's just hanging around till somebody takes the state. The next two states, task interruptible and task uninterruptible, are basically the states of where the processes are waiting for events, right? So they're both waiting, so there's a difference in terms of what one of them do, right? So task interruptible says that this task is waiting for something, waiting for I/O or something, but if you need to interrupt it for something, right, for whatever reason, you could deliver some interrupt. So you can kill the process, right? You can send a kill signal. You could send a timer signal to wake it up. You can interrupt what a task is doing, even though it's waiting for I/O, right? You must have noticed that in your C programs, implicitly, maybe not explicitly, right? If you read the man pages of most of your system calls, it'll say these system calls can be interrupted by a signal. So when you do a read, right? If you have your code to do sort of like this, right? And if you expect, and you start to do if. If you write a piece of code like this, where you try to read something using a read library or what have you, and if you get some count, then you have read to go through, and then you move forward, right? So there is another condition which you have to check if you're writing completely good code, which is this read can be interrupted, right? Meaning a timer or something can interrupt this read, right? So you could actually return an error code for saying the read was interrupted, and you are expected to reissue that read call, right? So you would have to write some code like if count equals, of course, in the right error code, right? You have to go back to here, right? How many of you do this stuff, or how many of you are aware that you have to reissue system calls after interrupt? Okay, so if you are not aware, be aware, right? Any of the system calls you look at will say it can be interrupted. If it's interrupted, it's up to you to reinitialize them, right? Most of the time, the interrupt that given to your process is a kill signal, Control C or something. In that case, what are you going to do, right? So you don't really care, right? And most of the time when you write these code, your program becomes really unwieldy. So you make a choice, right? So I believe the correct way to write hello world program is 1 or 2 pages long, right? Usually you don't do that because then the code is completely unreadable because it has all kind of stuff, right? But anyway, but for critical data structures, you would have to do that. For critical data structure, you would have to reinitialize, do the call. So if a process is in one of these states where it can be interrupted because something else came up, right? It's usually in the task interruptible case. If a process is in a state where it cannot be interrupted for whatever reason, so one of the reason is it's manipulating something inside the kernel. So at this point, if you try to interrupt the process and throw it out, right, then bad things is going to happen. So in that case, the process goes into a non-interruptible state, in which case it cannot be killed, nothing can be done. So it's going to stay in that state till it finishes, right? So the kernel can choose to put it into this state where nothing can happen to it, and it stays in that state till it can come out of it by itself, right? So if you use Linux or if you use any of these, any operating system, sometimes you'll see processes that nothing can be done to it. I mean, you cannot kill, you can go in a loop, try to kill it and stuff. Usually it happens when it's trying to wait for some I/O. If you're burning something or if you're using some hard disk or something failure, right? So you'll keep trying for it until that finishes, it won't let you go. So how many of you noticed this case where you have some processes that just cannot be killed, right? So few of you have noticed it, and so as you use your computers for this and other projects, you'll notice that processes go into the state rarely, not often, right? If they go into the state often, then system will be completely useless. But usually when something catastrophic happens, the kernel would not let you proceed because you're doing something important that has to either finish or it can't let you proceed. Right? So those are the two states. So if your process can either be on the interruptible case or uninterruptible case, most of the time you tend to be in the interruptible state. On rare occasions, it will put you in the non-interruptible state. So basically, this is the state diagram for the processes, which looks a lot like what we saw before. Basically, your process comes in, it goes between the two running states, either when it's ready to run and actually running, right? And when it has to do I/O, it either goes to the interruptible or uninterruptible state. When it's done, it goes into the zombie state. And once it gives the state to the parent, it goes away, right? So in a lot of sense, it's very similar to what we saw before, right? Except these states, there's the interruptible and non-interruptible state, right? So to create a process, Unix has three different ways of doing stuff. One is the fork we kind of talked about. There's the V fork, right? It's an abomination which should, like what the book says, should go away, right? I'll give you a little bit hint of why that's a bad thing to do. And then there's the notion of threads, right? Linux is fully aware of threads. In fact, Linux does not know that there's a different thing called thread, right? From Linux perspective, threads and tasks are the same. So if you share a certain amount, depending on what you share with the different tasks, it either behaves like a process or it behaves like a thread. And I'll show you how the clone system call would make that difference. But basically, Linux notion is creating a task is fast enough in Linux that creating a thread or creating a task are virtually the same, right? And so the other optimization, I'm not going to go through too detail into about what copy and write is, and we'll see that later when you do memory management. So basically the idea is when you do a fork system call in Unix, right, you're supposed to create a clone of your entire process. So you have to create an exact copy of what you're doing so that the other process, your child can continue from where it is, right? And usually we said processes do an exec, where they load a new program into the address space. So most of the time what happens is you would sincerely clone the parent, right? The first thing the child does is get rid of everything that was cloned and run a new process. So it tends to be fairly slow. So one of the optimization that you do is called copy on write. Basically you play games with the memory system and change the permission such that the child is not allowed to write into it. If it writes, then the OS knows about it, then it makes a copy. So it's a way of doing work lazily, right? So it creates two copies where the parent can continue to write into it. Sorry, parent or the child can write into it. When they try to write into it, you get a fault, right? And the kernel would make a copy at that time. So instead of making a copy all at once, it'll make it only when it's needed, right? And we'll see more of how this is done when you do memory management. But for now, this is a way of doing lazy copy, right? So the other thing that Linux tries to do is tries to run this child immediately rather than the parent, right? This is such that typically you expect the child to replace everything that the parent has with a new process, and typically you expect the parent to go off and do other things, right? So other things would mean that it can touch some of the data structures. So if you let the parent run first, then it's going to touch some data structures which may need you to do copies and stuff, right? So the heuristic they use is if you do a fork, let the child run. Most of the time, child is going to replace whatever the copy is with the exec, so you would do as little work as possible. So if you do all these two optimizations, right, then Linux fork is fairly fast. It's not that slow. So that's the logic, right? vfork is a call which comes from BSD operating system, Unix version of BSD, which was done back in the days when they didn't have the notion of copy and write, right? So in that world, when you do a fork, the child cannot touch anything on the parent, right? This is known to the programmer. So if you write a program using vfork, you know that the child cannot modify anything on the so you get a read-only process of the parent, but you're not allowed to modify it. In copy and write, you're allowed to modify it. If you modify it, things happen. In the V4 model, if you try to modify it, you get killed, right? And so all of them are implemented using the clone system call. In the next slide, I'll show you what the clone system call's different parameters are. So basically, clone would create a copy of the existing task, and depending on the flags that you pass, different stuff gets copied. And depending on what gets copied, it behaves like a thread or a fork. So Linux also has a notion of kernel threads, which run inside the kernel, which always runs in the privileged mode, which never comes into the user context at all, right? And they're only created by kernel threads. So when the system boots up, it creates a master kernel thread, which creates other kernel threads, right? And it can do processing inside the kernel. It can do cleanup. It can do account management and stuff inside the kernel, right? It'll do some processing. It'll wait inside the kernel. It never comes into the user state, and there are a few of them running in the background, right? So in terms of the clone system call, you don't have to remember all these flags, right? But remember that. So depending on how you pass the, what arguments you pass, the other clone shares something. So the first one is, it says the parent and the child would share the open files, right? Which is the model that fork uses. So if you're calling fork, you would cause it with clone files. But there are a whole bunch of other stuff, and they are used for implementing V4, used for implementing fork, and it's actually more powerful than either of those. So you can actually write code which can share just the right amount of stuff, right? So underlying, that's all Linux knows about. Yes?
Are there notes somewhere that can be patched?
Sorry.
Yeah. Yeah.
Okay, so so the next aspect of the process. So Linux has treats both the threads and the kernels, tasks and the threads the same way, right? Inside the kernel, it's all tasks, and depending on what you share, right, they get to. So different tasks could share different stuff. So if you are talking about a thread, it shares a whole lot more than if it's a fork process, right? But that's a distinction that you pass to the clone system call, right? So next comes scheduling. So Linux has to figure out how to schedule these different processes to get a better performance or what have you, right? So Linux is a priority-based preemptive scheduling system, which knows about real-time scheduling, right? So within the kernel, there are two notions of priority. There is the priority that you as a user can tell the system, right? And the way you do that is through a nice system call. And you can also invoke that using a system program called nice. So basically, that's a way of you telling the system what priority it should have. And this is defined by POSIX. It's a standard. So basically, the nice of a process can be from -20 to +19. The larger the nice value, the lower priority you get, right? So the highest priority is -20 nice, and the lowest priority is +19, right? And Linux also has a notion of real-time priorities which are absolute, meaning so they're from 0 to 99. So whatever priority you get, you are assigned, right? You are above the normal process priority, and it stays there, right? Whereas for the nice priorities, it's one of the inputs to what the system decides to do. So Linux is trying to be a general purpose operating system. So it does not listen to exactly what you ask for. So if you ask for higher priority, it keeps that in mind while it tries to balance its other goals. If it's a real-time process, it gets out of the way and trusts whatever you said is accurate, right? So once it has the process priority, once it has this nice value, right? If it has two processes, it has to figure out how much of the CPU it gives to each one of those, right? It has to keep a running total of how much it's trying to do. So if it's doing some sort of a round robin kind of scheduling, it still has to figure out that in the long run, how much it's giving to each one of those, right? Remember one of the exams, the question in the exam was how to give more CPU to certain processes. So if you want to do that, how would you do that, right? So how would you give for higher priority processes more CPU, lower priority processes less CPU, without actually changing the quanta in which each one of them are offered? The way you do that is through the notion of time slices, right? So basically the kernel figures out, based on all the processes in the current running queue, right? It figures out how much each one of them are worth, right? So it calculates a time slice value, right? Which can be, the lowest one can be the time slice that you compile a kernel into, which is what you did for a homework project. And the upper one can be 800 millisecond, right? So it can decide, if there are two processes, it can decide that one of them is a low priority, another one is a high priority. High priority task would get the maximum, could get the maximum 800 millisecond. Low priority would get whatever you compile the kernel to, let's say 10 millisecond, right? So what that means is, and the other stuff is, if there exists a process which can run, which has a time slice left, no other process can be scheduled, right? So if this is the only thing which exists, there's one with 800, one with 10, right? The first time slice, let's assume it gives the 10, right? So the second time slice, it has to give to the 800 one, and it has to keep giving it till that 800 goes to 0, right? Till that process is completely runs out of time slice, no other process can run. So basically, whatever time slice is allocated, it'll keep giving to that process, right? So until the time there exists some process which has a time slice which can run, right? It'll keep getting CPU, right? And once it runs out, you do recalculation. You kind of look at what the processes you have, what the priorities are, calculate what the time slice each one should get, and then you let them go, right? So it maintains two queues. One is exhausted, one is the active queue, and it does some. It doesn't exactly implement this, in order to get better interactive performance. So, for example, if you have interactive task, if it figures it's an interactive task, and you lose all time slices, right? Even if you don't have any time slice, it puts you back in the active list, because otherwise you have to wait for the 800 milliseconds before you can get some interactive performance, which, though not fair, on a desktop is much welcome, right? So if it thinks you are an interactive task, you will still get to run even though you don't have any time slice left, right? The assumption is, if you are an interactive task, use a CPU less. So it's a trade-off between responsive system and your policies, right? The other thing you have to worry about is, if this is done naively, right? If you're trying to do this naively, what you would do is, at the time when things get exhausted, you would look at all the tasks in the system, trying to figure out what the priorities are, and trying to figure out how much time slice they should have, and then let it go, right? And it could be a long process. So potentially you can have up to 32,000 processes. So you don't want to be going through this list all at the time when time slice has run out. So what it tries to do, it tries to calculate them when it puts them in the exhausted list, right? So it figures out what the priority is for the processes which are currently running, right? And assigns them a time slice of what they would get in the next slot when they're put in the exhausted list. So when you really exhaust the space, you basically switch the pointers, and you move everything in the active list to exhausted list, and so on, without having to do extra calculation, right? So you amortize the cost of calculating this time slice throughout the scheduling, and not in one shot, right? And this is part of the O of N1 operation that Linux tries for, right? So how many of you are aware of this big O notation? Oh, excellent. You'll actually go through a lot of that in your theory of computation course, and so I hope you understand the difference between O of 1, O of N, and so on, right? So it depends on how much time it takes and how it relates to number of processes. So O of 1 basically says it's constant, right? Whatever operation it has to do does not depend on the number of processes, and O of n squared depends on the number of processes to certain multiples, right? And you also are aware O of 1 does not mean it's small, right? O of 1 only means it's a constant, right? So practically O of 1 may actually be more than O of n for n equals 100, right? Because we're talking about different constants and different numbers. So you have to make a judgment whether O of 1 is better than O of n for your particular system, right? Regardless, Linux tries to implement O of 1, which means that the time it takes to schedule a new process does not depend on the number of processors in the system, right? So in that model, right, since it's trying to do priority scheduling, right, so if it has n processes in the system and it has to run the process with the highest priority, right, and within the process of the higher priority, it has to run them in sort of a round robin, right? So if you have to do this, so it's basically if you think of it as an array, right? So if you have to go through the array and trying to find out what's the one of the highest priority, right? So you can either do that by keeping this array sorted by priorities or what have you. Linux tries to use a fairly nice data structure called priority arrays to make it O of 1, right? So basically, it keeps a little table for each priority, right? And it maintains a bitmap where if a process gets assigned to a particular priority table over here, right? If it has to add an entry, it'll set the corresponding bit on the priority mask, right? So for example, in that particular figure, right, bit 0 is priority 0 and goes on so far. So the first black dot thing is priority 7, right? Which means that there exists a process in the system right now which has a priority of 7, right? So it could be more because that's what this table talks about. So when it has to do a schedule, it quickly looks at this priority bit mask to try to find out which is the highest priority that is set. So it has to start from here and look back on a bit field, right? And so every machine, every different architecture has to implement a fast way to do bitmap manipulation to find out which is the first bit that is set on this bit array, right? And depending on the architecture, it can either be fast or slow, but it's constant order, right? It does not depend on how many processes there are here. It only depends on the size of the array, right? So using this, it can figure out, so when it tries to schedule a new process, it can go through this bitmap, try to figure out which is the first one which is black, which is the first one which is set, go to the particular table, look at get the next process, and then run it, right? So it can do that fairly quickly. So it implements priority scheduling across a number of priorities by using this data structure in constant time, right? So it does not depend on the number of processes in the system, right? And there are other nice things about the Linux kernel that you all probably work on, the 2.6 kernel. It's fully SMT, it's fully symmetric multiprocessor, which if you remember means that if you have number of processors, right, each one of them does its scheduling independently. So each one of them can do processing independently. So the kernel virtually runs on each one of them. So a process can run on any one of them, and the kernel services can be run on any one of them. So there are multiple independent queues running each processor, right? So if you have 4 processors, there are 4 run queues. Each processor looks at one run queue and puts tasks around, right? But if you do that, then there's possibility of load imbalance, right? And there's a possibility of not doing a good job with affinity. So it tries to balance both, right? So each processor gets to look at its own run queue, but they also try to manage, try to balance these processes. So for example, if a processor is idle, right, it'll look at other processors run queues to see if any one of them has any job. If they do, it'll pull it, right? Yes?
When a new process is created, how do they decide which
So it,
processor go to.
that's the excellent thing. So when you create a new task, right, you have to find the one which has the lowest number of tasks, right? So if you think about it, maybe it's not the best way to do this stuff, right? So we talked about notion of, I/O intensive tasks, CPU intensive tasks, and mixture, and so on. So if you have multiple processors, what you really want is try to find the one processor which has the least amount of load for a particular CPU, right? So if you have one processor with 2 tasks which are CPU bound, and one processor with 2 tasks which are I/O bound, that's imbalance, right? Because this one is going to use all the CPU, it's going to wait. This one is not going to do a good job and stuff. It doesn't do that. It doesn't try to do that. It basically looks at the count. So if both of them are 2, it figures out 1. If one of them is 2, one of them is 3, it puts them in the 2, 1, right? And then it tries to look in the long run, trying to balance these things. These are active area of research, and you're trying to figure out how you would balance these things, right, without affecting affinity and all those things, and still do a decent job, right? And that's why you see different versions of kernel coming up, because somebody has a better idea, they try it and then see if it works out. So the other thing it tries to do is, so if it has to pull a task, right, pull a task from other processor, other process may have affinity to that particular processor. So you try to pull processes which are least disruptive. And one of the ways to do that is to try to get stuff from the exhausted list. So if you have some task on the exhausted list on another processor, that means they exhausted their CPU. So they've been waiting hopefully for a long time. So when you move them, right, they'd be happy to continue and be least disruptive. So you try this little tweak and see how that works out, kind of stuff. So basically, it tries to manage the global load while each one of them on the, at the short-term scheduler basically schedules everything within its own run queue. Long-term, it tries to see how it should do the load balancing, right? It tries to do better affinity. It's not where it should be, right? So some of the commercial operating systems like Silicon Graphics and stuff do a much better job of affinity. They do a much better job of keeping processors where they should belong to the processor close to the data, right? Linux has ways to go on that one. So it keeps track. So it tries to differentiate between CPU-bound jobs, interactive jobs, and CPU-bound jobs which run rarely, right? So it does not only keep track of how much CPU you are using, it also keeps track of how much CPU you used in the last time you were allocated a time slot, right? So if you have a job which is fully CPU intensive, you'll use all the time slot. If you have a job which is interactive, you'll use very little CPU and then give up its quanta. If you have a job which basically sleeps for a while, wakes up, and runs the CPU, uses the CPU for a lot, and then goes back to sleep, right? So it will behave somewhere in the middle, right? It'll behave like a CPU-bound job because the calculation it does, it tries to figure out how much of the CPU that you allocated you actually used. So if you use all the CPU, even though you didn't use anything for a while, right, you still don't get the same kind of benefit as an interactive task, right? So it tries to manage these things. So it tries to manage these things such that it's fair, and it does not let some application writer to game the system to get more resources than they should, right? So it seems to work fairly good, right? And it's an ongoing thing of people trying to change this. And the kernel is fully preemptible, right? Basically, any kernel can be stopped at any point, except when it's holding some resources. So when it's doing something critical, nothing can stop the kernel. But other than that, kernel tasks and kernel threads can compete for resources just like anything else. So they can lose a CPU, they can be preempted off. So it also implements the real-time scheduling through 2 queues, right? One is the sched FIFO and sched round robin, and FIFO is basically round robin with infinite time quanta. So these are above the sched normal, right? So if you have any task which is willing to run in sched FIFO or sched round robin, right, they take precedence over normal processes. And So when they're finished, then the normal processes run. So it's fundamentally like two operating systems. So when you have a real-time task running, the whole system would not do anything else, but when they finish, you get to the normal one, right? So technically, they can only guarantee soft real-time, because they cannot guarantee that you'll get absolute performance, but it's fairly good, right? So we have a separate course on real-time systems. So real-time systems, you're not worried about how fast the system is. You're mostly worried about predictability, right? So I have to be able to say, if I press this lever in 10 milliseconds, that nuclear power plant will be shut down, right? I need to be able to guarantee that, right? So one of the steps towards that goal is the O((1) schedulers, right? So if you can go through this kernel and say, if you press this button, this is what has to happen, right? Your process has to be running in this priority, and I can predict how long it will take for me to context switch. I can predict how long it will take for me to run the scheduler, everything, right? So if you use O((n), it's not good, because then it means it depends on the number of processes. If it's O((1), then I can kind of predict how much it should be, right? So that's the steps you need to take to make it closer to a hard real-time system. But Linux still cannot technically be a hard real-time system. So it's a soft real-time system, which is fairly good for most users, right? So most of these functions are in the file, kernel/kit.c. It's a fairly long file, right? But it should be easier file to understand, because this is at the core of most of what Linux does, right? So it's been seen by a whole bunch of programmers and students and everybody alike, right? So most likely the code should be fairly simple, straightforward, and easy to read, right? So if there's any one code that you should look into the kernel, these kind of codes are probably it. The code that you probably would find it a lot more complex are windowing systems or device drivers, which are not used by as many users, right? This is the core of Linux. So I encourage you to take a look at the code. It's not going to be on your exam and stuff, but it's a good way to see how whatever you looked at translates to some of the real systems out there, right? So that's all I have for today, and we'll continue with the next module tomorrow.